Okay, looks like we're live and we are streaming. So we've gotten really far. We've created a new algorithm that combines sensitivity encoding or sense with linear predictability like greppa or SPIRiT. Okay. And so what to do now? We might just play with it a little bit, see how well it performs. We might add in compressed sensing, which might be the most fun thing to do. Guess we're about to find out. Okay. Could profile it. Let's do that. Off it goes. Now this, we're loading the S maps that make sensitivity maps created. So one thing I want to do almost right away is just take away this line of code completely. And in this MATLAB file, stuff.mat, I want to replace it with the S maps calculated using Pisco. It's currently taking about 50 seconds. That's with a whole bunch of print statements, of course. The bulk of it's in apply W, which is taking 30 seconds. And between FFT2 and IFFT2, it's taking 15 seconds. So what's happening in apply W outside of these FFTs? So it's just these circular convolutions. And the adjoint's taking more than double the time of the straight operation. This is taking 22 seconds. This is an apply W. Now that we've got more of the code figured out, let's see what happens. Okay, so first things first, let's do what I just said. Okay. Now SMaps is being loaded out of stuff.mat. And, ooh, we're going to need the support. Now we could comment out that code and delete that. Okay. We have a call to recon SPIRiT here and here, so we'll just delete this one. Looks like we don't need the ACR either because that's just using call Pisco. I think we did this already. Let's see if that makes it faster. You're first going to make sure that we didn't change anything with do checks. I use do checks a lot, don't I? Very, very handy. Failed. Okay, that's why we do checks. I don't know that this is right. I haven't thought about this at all. Pretty early, honestly. So flip W is 4-dimensional. And in is 3-dimensional. We're going to do the 2-dimensional convolution. So now out is 4-dimensional. And I don't know which of these, I guess is the, it's that. So why didn't that work earlier? Here we're summing over the 3rd dimension. Okay, here's what I'm going to do. I get rid of this sum. Let's just make sure the circular convolution passes do checks. Same number of elements. And here we are again, back to something simple. It's 256 by 256 by 8. We're going to apply W. Okay. So here in is 3 dimensions. It's going to output a 4-dimensional thing. So now here, we're inputting something 4-dimensional. But for the adjoint, this has to output a 3-dimensional thing. So what is that 3-dimensional thing? just for the circular convolution now, I'm not considering this part. I think we sum along the fourth dimension. That's my guess. Yep. Okay. So the adjoint of the circular convolution is just this summed along the fourth dimension. But that means that this is not quite right. So if K has fewer dimensions than A, in the adjoint, you have to sum along those dimensions. I suspect the same is true in reverse. But what if, this is pretty tough. When I input transp, when I set transp operator to transp, I want the output of this to be the adjoint of whatever its input would have been. I think this is right. If n dims of A is less than n dims of K, else if n dims A is greater than n dims K, else do nothing. How does sum work? Dim. Whoa. Vec dim. Well, sums the elements of A based on the dimensions specified in the vector. Good. Good. That's what I wanted. So how do I do that? Now the thing is, this could be weird. Like, the question is, what dimensions does BSX fun operate over? And we have to sum over the other dimensions. Do we know that? Does BSX fun return that? No. So if I do it this way, if I sum over the greater number of the dimensions, it's going to assume that, well, that's the only way it makes sense, though, because we're doing FFT2s. Okay, so I think this is going to work. Sum out is equal to sum. Actually, I don't need this if statement. Out. I could say and n dims A is not equal to n dims K. I don't know that I need this, but it doesn't hurt to put it there. Max n dims A and n dims K to and dims out. Use of brackets is unnecessary. If I have that right, and there's no reason to believe that I do, then I should no longer need this sum. Let's see what happens. Just 4. What? Oh no. Is there any way to know? The issue is that right here, flip in W is the same as, it has the same number of dimensions as in. The only reason that we know to sum is because on the straight transformation, we knew that flip W was more dimensions than in. Okay, which means we're going to have to tell it. Okay. So we never use op. What do you guys think? Think it works? Apparently not. Huh? Oh. Inputs to the dot product must have the same number of dimensions. Okay, so let's see what's happening now. N-dims out is 3. N-dims out is 4. This should be 3 plus 1. Doesn't even get there? That's weird. Oh. Now we don't have to do this. And we could just set this to something like this. I think that's right. Three, right? Okay, so now out should be 3-dimensional. I'm guessing check W should pass now. And it does. Good. Okay, so we made cert comb a little bit better. Now the issue is at this point, out is 4-dimensional, and we're going to reduce it to 3 dimensions. The adjoint of a sum in a dimension, I think, is retmat. Pretty tough. Yeah. Doesn't even get that far. Do I not have a breakpoint here any longer? Let's dive into check adjoint. Three dimensions, 3 three dimensions, but 64. Okay, this is 256 by 256 by 8. That's weird. First of all, so F here is applied W, no transpose. So FX1's I would have thought was, okay, so then I'm wrong. At this point, out has 4 dimensions, and we're going to sum over one of them. Okay. At this point, out has 3 dimensions. We know that this is the adjoint of this. Oh, I got to reverse the order, of course. Here now, out is not 4-dimensional. So in is like that. Now out should be 4-dimensional. Okay. Let's make that in. It's just a reshape and a wet mat. Now out should be 3-dimensional again. The issue is that, I don't know. I doubt this will work. Let's just see what happens. Oh my goodness. I guess it had to work. Because we knew the circular convolution was the adjoint, with transpose the adjoint of that. So we just needed the adjoint of the squeeze sum, which is reshape ret mat. Okay. So we no longer have this loop here. Did that actually help anything? I think it was taking like 50 seconds before. Now it takes 600 seconds. It can't be right. I mean, it didn't just take us 10 minutes to run that. That didn't happen. So I think because we called profile on so many times, something weird happened. Let's see again. "40 seconds. Flight W is taking 26 seconds. Before this was taking 22 seconds, and now it takes 15. Okay, 7 seconds gone. That's better. Also, circular convolution, the adjoint is correct. When we pass in A and K of different dimensions, if we also specify n dims out. So let's check it in. Now, of course, phi W is also in spirit, right? Can I just take this and put it here? Squeeze some. Adjoint passed. MATLAB, I think, has just-in-time compilation, so I'm hoping this line compiles out to be faster than having them on separate lines. Who knows? Okay. Hmm. We don't have S image here. We have MN. So there was this issue that it looked like the SPIRiT reconstruction was doing better than Recon SPIRiT Reg. That is a nice result. I'm looking at this little bit here, and I'm wondering if that's true or not. Maybe this too. Because it looks like the muscle protrudes out of the skin, and that just can't be right. Fly W, 28 seconds, 61 seconds. Doesn't seem right, does it? So here's true. Oh, it does look like that. And sure enough, these things are here. Yeah, spirit reconstruction is really good. I wonder why it looks like that in true, but that's not anything I worry about. Like, if that's what the data is showing, then I'm just trying to replicate the data. Now here's something. Nope, never mind. Those look really similar, don't they? It's just with 20 reconstruction with 25% of the data. It's astounding. Down to 36 seconds, apply W is taking 26 seconds. And if we go back here, this hasn't changed much. So it looks like the two lines didn't matter. This is still at 16 seconds, 15 seconds. Seems to be like what we've got. Okay. And now we've got it in spirit and everything's working. So optimization and apply W2. All right. Boom. This IFFT shift is taking 3 seconds. Where does that happen? Inside of circ shift? That's a link, but if I click on it, it does nothing. That's strange. Okay. Let's see what we got on our to-do list. What do you say? Oh, maybe it brought up this. Okay. Oh, I see. This is the line that's taking so much time. Okay, so when I clicked on that, it brought that line up in the editor. I want to see how many of these to-dos that we've got. Vectorize loops and apply W, gone. Preconditioning, gone. Add compressed, not preconditioning, but what was it? Non-rectangular field of view, gone. I don't know how to add preconditioning quickly. I don't know how to make it efficient. If it's not efficient, then what's the point? Maybe to make the reconstruction more reliable with different step sizes. not going to worry about that now for now. We can add in compressed sensing. What would that look like? This doesn't take into account the data consistency. It's not explicitly in there, right? So what is this? It says minimize the L1 norm of the wavelet transform of X, subject to this constraint and this constraint. It would complicate this code a lot to add that in, because we need a different A. We need an A that takes into account the sparsifying transformation. Another thing is that my implementation of W is limited. I should really change this to use convolution. But I could get this working. How long have we been streaming? Can't tell how long we've been streaming. About 45 minutes. Another thing, what if you wanted a different sparsifying transformation? In particular, what if you wanted a like over complete, or maybe this is right. What if you wanted an over complete transformation comprised of wavelets and curvelets, which should do better. They're like sparse coding, right? What if you wanted some other transformation? I guess I could just allow for an argument that is this sparsifying transformation and make a default that's something simple like the Debouchet for wavelet transform. The proximal operator of this with an orthogonal wavelet transformation is simple, and so you can make it F. But if wavelet is not orthogonal, then then this proximal operator is not simple, and then we need to make wave a part of A and put this into the G function. As you've seen, SPIRiT works well. Like, do we actually need data consistency, which needs sensitivity maps? I think there should be a PT here. Okay. Boy, oh boy. Let's implement this. Nope. Let's implement this. And later we'll add a parameter for the sparsifying transformation. And we're going to put it all in G so that if you provide a different sparsifying transformation, it's not orthogonal, then it'll still work. So F is going to be the same. Okay. How will we know that we're doing this? Well, because gamma we're already using. Someone could supply a noise bound, but like here, the beauty of this is that we can determine the noise bound automatically. I think we're going to have to tell it. Gamma support lambda. A little confused. S snaps is required for this code. certainly right now. Now it needn't be, right? Why not? Because we're using a non-rectangular field of view. So if S, we could do this for just a single coil data, and that would be equivalent to S being just the identity matrix. Alternatively, if we don't provide the sensitivity maps, we could just solve these problems individually for each coil. Well, I don't know. This is really, that gets complicated. It seems like S maps is just a fundamental part of this code, which is very, very fine. The only thing is that, you might want to solve this problem for a single coil and assume that S is the identity. I'll worry about that later. Okay. We're back here to minimizing over a sphere. I guess we'll do CS by default, right? Did I actually do that? Yes, I did. Because I was dividing by the number of pixels. So we're going to do it here again. Now here it's not the number of pixels. But the number of elements in B. Okay, so we are minimizing over a sphere. The sphere is, we're now minimizing over two spheres. This one and this one. So it's going to be the intersection of those spheres. But it's no longer a least squares problem. We've written a lot of code, haven't we? Spirit reg min over sphere. Okay. G. If numL, nope, if CS is equal to true, out equals out plus G3 of N3. So this is no longer end. We're going to have to fix that. What is G2? For each coil, we're going to do an indicator function. SK data. G3 Okay. So we've added that into G. Now let's add it into A. Could of course do this. That's fine. A is beyond minimization over a sphere, isn't it? All of these things have W minus I. And so we have included that in A throughout. How did we do LSQR? LSQR uses apply A. That doesn't seem right because I don't think this is going to run actually. Have we even run this? Lambda equals 0 and gamma is equal to 0. So this really is SPIRiT reg. Now, if lambda is equal to 0 and gamma is equal to 0, then we want it's hard constraint. Oh, if lambda is equal to 0. Okay, I remember now. We struggled with this for quite a lot. What if lambda is equal to 0? Suppose somebody applies lambda equals 0 and gamma is equal to 0. What does that mean? Well, that could mean with lambda is equal to 0, this term goes away. But so the regularization term that would be here is gone. But this means like since this is a norm squared, it's non-negative. And so if we set this equal to 0, it means satisfy that exactly. Now that's probably infeasible, but that's what it means. Little tough, little tough. Maybe the thing to do is just eliminate LSQR from this code. We already have a model-based reconstruction. This is LSQR without SPIRiT regularization. This code is SPIRiT regularization. And what's happening is that the combination of parameters being used to choose each of these optimization problems is becoming difficult. Now, if someone provides lambda equals 0 and numL gamma is equal to 0, you'd think you were doing LSQR. Seems right. How do I do that? Because apply A, so we could take advantage of these subparts of apply A. LSQR here, it's not apply A we want, but apply MFSPT. Yeah. Which I can do here. So if do LSQR equals true, then we don't need the rest. You can put that code right there. Don't have image 0. Make image 0 and then return. So now we just need to do LSQR. Okay. If num L lambda is greater than 0 and lambda is equal to 0 and num L gamma is equal to 0, then do LSQR. Now we don't need to do any of this stuff. We just need MFST. MFSPT, sorry. We don't need any of this stuff if we're doing LSQR. Apply P. It's the only place square root of lambda is used. Applied, yep. W n minus I. Okay, this is getting cleaner actually. We need P for MFSPT, of course, so we'll define it before. Now we've got M. Ooh, apply W. I don't need that. Apply W minus I. Where's M? We don't need the ACR. There's M. Wait, how did... Okay, right. Let's find W. Uh-oh. Where's apply W? Oh, there's find W. Good. Okay, so this is nice because if we're doing LSQR, we don't even need, okay, still going. Where does gamma get used? Max gamma. Still cleaning up some code. Right now we're going to clean up this gamma stuff. Okay. We only need this if we are not doing LSQR. If do LSQR. Okay. Now we come here. If numL lambda is equal to 0, do we actually have that? If numL lambda is greater than 0 and lambda equals 0. Okay. So now we're down here. If numL lambda is equal to 0 and numL gamma is equal to 0, then we want to find gamma. What does it mean to find gamma? It means this. Else we don't find gamma. So we do this. And then what do we set gamma to? Let's do a check up here. If num lambda is greater than 0 and num gamma is greater than 0 and there is no problem that uses no optimization problem. Okay, how about this? You cannot specify both lambda and gamma. And there's no reason why you would. Okay. Else if num lambda is greater than 0 and lambda is equal to 0 and num gamma is equal to 0, then do LSQR. I don't see. This is a check, and I know that this, if this runs, then this will never run, but that's true anyways because this is an error and this seems cleaner to me. These are the conditions for LSQR. Never mind, we're going to keep it like this. All right. All right. Where does the support come in? Comes in right before P, right? MFSPT. Ooh. Now we're setting image 0. And then we call it LSQR. If we call LSQR, if it's appropriate, if do LSQR set. If not, then we go on to all this stuff. And this is much better. Now we create this apply A. Okay, now this is a little weird because we've got some do checks here that we would only use if we were doing LSQR. So let's put those do checks there. If do checks equals true, and at this point we have MFSPT, right? Okay. Now we come down here. We can do all those checks. We've got find W, which we believe works. Let's see if this even runs. Nope. Lambda. Do LSQR equals true. Okay. Else do LSQR equals false. The next time we see lambda or gamma is at find W, so we don't need to set them if we're setting do LSQR. So do we even need that? Do we need do LSQR? I don't think so. If the conditions for LSQR are set, then we do LSQR. LSQR failed. User supplied function failed. Failed. Why did that fail? Let's make sure do checks passes. We're not supplying a support? Because we're just doing it there. Okay. Yeah, we didn't have support when we wrote that line of code. Okay, good. Now we've got a bug here. Here. $256. Apply P trans. Right, okay. So let's see. Apply P transpose. Ooh, but support is empty, isn't it? Okay. Well, all right. If there's no support, then P is just... Actually, it's even cleaner to do it this way, maybe. And support. That's not used there. So we're only going to call P when the support is greater than 0, so we don't need an if statement in here, and that's better. Got it? Just doing code cleanup right now. That's all that's happening. That works just fine now, even though the support is not supplied, and that's great. So actually, I'd like to check this in. There's this G3 thing. It's yes. I guess we'll start out with the default for CS equal to false. Let's see if that runs. Gamma. Seems to be running. Been at this an hour and a half now. Yeah, very good. So I could either go on to implement CS, or I can just check in what we've got as code cleanup after removing the CS. Go on with life. Guess I'm not doing that. So psi is going to be the name of our, I guess we'll call it W. W in is, we already have a W, right? Psi in is equal to psi in. What are the Greek letters? I want uppercase and lowercase. Okay, so the sparsifying transformation is generally represented as capital psi. That's what we'll do. I haven't implemented psi in, that's fine. Ooh. This is going to be a bit tougher. I think that's right. So what's happening is now G2 is different. Pretty tough, pretty tough, pretty tough, pretty tough. Okay, not doing this today. We've made some serious headway. That's where we're going to stop. we're going to think harder about how to implement compressed sensing if we do it. Because I thought, since we have to change G2, maybe the right thing is to make a whole new function here. Rather than minimization over a sphere, we'll just have MRI recon spirit reg G compressed sensing. Let's make sure it still runs. So we had a bug. LSQR wasn't working before. In order to get that working, we cleaned up the code quite a bit in a really nice way. So now we don't even create functions. We don't have to create if we're just calling LSQR. And we better determine when we need to call LSQR. If lambda is greater than 0 and numl, if lambda is equal to 0 and numl of gamma is equal to 0, then we call LSQR. So that's good. Okay, so we did an optimization today, and we did some code cleanup, and we fixed the bug. And that is a remarkable similarity. We're using the support now. So you see here, I'll show you. You see how this portion of the leg gets cut off? That's because the support was wrong. The support did not take into account, did not find this for whatever reason. I don't have a better way to make a support, I don't think. I have a function called MRI make intensity mask, and sometimes it works and sometimes it doesn't. This is probably really good, the support that we're doing. And if we like window it down quite a lot, you'll see we don't have any noise outside of the support. This is that aliasing of the support down here. The reason this is brighter is probably because of the region here that was cut off with the support. So this is really nice. I didn't know Pisco gave us the support, but I'm really pleased that it does. Significant code cleanup. And so another question that we'll have to ask ourselves is, are we really going to let a user choose all of these problems? For example, I might not want spirit regularization. I might just want compressed sensing. Is that a part of this code? If I supply a noise bound, or if I say CS is true and say numl of gamma is equal to 0, does that mean automatically find gamma? Or does that mean, that's what it would mean to me, actually. So this is really a spirit regularization code right now. Spirit regularization is always included unless we set lambda to 0. And the reason we're using LSQR instead of the Tikhonov regularization for that is because it's more efficient. But we really are doing this, which is spirit regularization with lambda equals 0 when we set lambda equal to 0. I don't know. This is getting hard. It looks like spirit regularization is a good thing. I suspect that if we push this harder, let's do it now. Here I'm pushing it harder, so I'm taking every third column horizontally and every third row vertically and every other column. I suspect then that spirit, at some point, I believe if we push it hard enough, then spirit will not do as well, especially now because spirit's the kernel's only 5, whatever. Spirit will not do as well as this recon spirit regularization. I suspect that's the case. And it looks like we're about to find out. Now, this is legitimate. Like, this is a real test, but normally I would want to make sure that the center index is sampled. Okay, so now spirit's starting to fail. You see all this noise in here. Let's see what spirit regularization does. You might say, what if you made the spirit kernel larger? And that might work, but the larger you make the spirit kernel, the more you're assuming that linear combinations of the sensitivity maps combine into complex exponentials of higher and higher frequencies. Here's spirit regularization, and that looks significantly better, doesn't it? And that's why we did this. Like the noise here, the noise here. Spirit regularization is doing much better now. Okay. So I think I've talked myself into thinking of this code as a spirit regularization code. I think we are going to add in compressed sensing next. And I think we're just going to create a function called spirit reg underscore CS. And if that's the case, do we want to keep any of this? Where's G1? I don't think so. You know, G1 is the same, so we could presumably create one G1 and pass it into both minimization over sphere and CS, but we're just not going to do that. So we'll leave that probably for tomorrow. Made some good progress today. See you next time.